All right. So we've been mentioning the greenhouse effect for a couple lectures now. So how does this work? Let's get into the nuts and bolts here. Um, we talked before about how the temperature of any planet is determined by that thermal balance, that the energy in from the sun has to be balanced by the energy back out into space, and that a planet will heat up until it is able to come up to the luminosity. We haven't really thought about luminosity of a planet yet, but it is essentially that a planet will warm up until its heat re-radiated back out into space balances the energy that it absorbs in from sunlight. And now, not every photon of light that comes from the sun is going to get absorbed by a planet. A planet can also be reflective, right? That there are lighter colored parts of the Earth, like you can sort of see from this photo here, um, ice caps, clouds, light colored deserts. Those are very good at reflecting light. And so the dark colored areas, like forests and jungles and the oceans, um, those dark colored areas are going to be the parts that are absorbing the light. So the albedo of the Earth is about 30%. The other 70% gets absorbed by the Earth. That 70% of the sunlight is what's heating up the Earth and bringing the Earth up to temperature until the energy out equals the energy in. All right? And if it were just a matter of light getting absorbed by the surface and light radiated off the surface, then we would just have the effective temperature model. If a planet has an atmosphere, though, an atmosphere is, well, in the case of a terrestrial planet especially, an atmosphere is a low density gas and it's relatively cool. It's not a hot gas, it's a cool gas. And so what does a cool gas do with light? It absorbs it. And so as that light travels through the atmosphere is going to absorb light. But remember how absorption spectra work. A low density cool gas will only absorb specific wavelengths of light based on what molecule of gas it is. And so there's a lot going on with this graph, but let's unpack this here. Um, Here is the top graph here is the spectra of the sun and the spectrum of the Earth, right? So let me draw some lines here to understand. Right? Here's the black body spectrum of the sun. The sun's giving off a little bit of ultraviolet, a lot of visible, and a lot of infrared. Here's the black body spectrum of the Earth, right? The Earth is cooler, but the surface of the Earth is a warm rock, and so it's going to give off its own black body spectrum. But the Earth is not hot like a star, it's just warm, and so its spectrum is pretty much all in the infrared. All right? So this is the spectrum of light that is shining through the Earth's atmosphere. The light that is coming down from the Earth and the light that is radiating up off the Earth, passing through the atmosphere and then trying to get back out into space. Okay? Um, all the rest of these graphs are the absorption spectrum of the gases. So each of these graphs is a percentage, the percentage of light that is absorbed versus the wavelength of that light. And so most of Earth's atmosphere is made of what? Nitrogen, right? We don't even put nitrogen gas on this graph because nitrogen gas is a really weak absorber. The absorption lines are so weak, they're not even worth talking about in this context. Some of the nitrogen and the oxygen in the Earth's atmosphere gets together and forms dinitrogen monoxide, which has a few weak absorption lines in the infrared, but it's pretty weak, not much. Oxygen is the other major component of the Earth's atmosphere, and most of the oxygen that we breathe to stay alive, most of the oxygen is O2, right? It's a molecule made of two oxygen atoms. Some of the oxygen in the Earth's atmosphere is O3, also known as ozone. And so ozone, like the ozone layer in Earth's atmosphere, is a really good absorber of ultraviolet light. So the oxygen in the Earth's atmosphere, specifically the ozone, is a really good absorber of ultraviolet. But then there's not that much ultraviolet coming through the Earth's atmosphere. So that's not, you're getting almost 100% absorption in the ultraviolet, but there's not that many. You're getting 100% of not much is not much. There's a little bit of absorption in the visible spectrum, pretty weak though, and a few absorption lines. Each of these spikes is an absorption line, right? So a few absorption lines in the infrared. Again, that's most of the Earth's atmosphere. Most of Earth's atmosphere is nitrogen, oxygen, and a little bit of that dinitrogen monoxide. That's 99% of the Earth's atmosphere. And it doesn't absorb a lot of light. These are very weak absorbers. Carbon dioxide, though, there's a little bit of carbon dioxide in the Earth's atmosphere, and carbon dioxide has these big absorption features in the infrared, and there's a lot of infrared passing through the atmosphere, both the infrared coming down from the sun and the infrared coming up off the Earth. So actually, carbon dioxide absorbs a lot of light. Water vapor is an even stronger absorber, right? Water vapor has these big absorption lines all throughout the infrared spectrum, and there's a lot of infrared light. So when you add all of these gases up, here's the total absorption spectrum of the Earth's atmosphere. Lots of absorption in the UV, but there's not that much UV. Weak absorption in the visible, which is how we see, right? We can see through the Earth's atmosphere. We can see out into space. We can see the stars. Starlight shines through the Earth's atmosphere, and we can see the stars because Earth's atmosphere is very transparent in the visible spectrum. And heavy absorption in the infrared, and there's a lot of infrared light. So most of the absorption of light by the Earth's atmosphere is being done over here. It's absorption in the infrared. This is what gives rise to the greenhouse effect. Because what's happening here, right? You got the Earth's surface, here's the Earth's surface, here's the Earth's atmosphere, here's out in space. And what happens? Well, light shines down on the Earth from the sun. Now, I've color-coded. Visible light is yellow, infrared light is red. I haven't really drawn an arrow for ultraviolet light because there's not that much of it and it's not that big of a story. So when that light, right, the visible light gets through the atmosphere and it hits the Earth's surface, right? Most of the infrared gets absorbed by the atmosphere, but the visible light has an easy time. The visible light from the sun has an easy time getting through the atmosphere. It hits the Earth's surface, it warms the Earth's surface up. If the Earth's surface warms up, then the Earth is going to start giving off its own black body spectrum. And what kind of light does the Earth emit? It's also infrared, so hence the red arrow. But it can't get out, right? These gases in the Earth's atmosphere, specifically the carbon dioxide and the water, the carbon dioxide and the water are what are called the greenhouse gases. So what is a greenhouse gas? A greenhouse gas is a gas that is really good at absorbing infrared light. So these gases, the carbon dioxide and the water vapor, they're absorbing the infrared light coming up off the Earth and the infrared light coming down from the sun, and they're absorbing that energy and bouncing it around. And it just stays, right? Let's say this molecule absorbs some infrared. And then when that molecule absorbs light, what happens to it? It warms up. And so it gives off that infrared light. That infrared light is emitted by this molecule and it bounces around and runs into this molecule. And that molecule gives off the infrared and gets absorbed by that one. And this molecule gives off the infrared. So basically, these molecules are so good, these greenhouse gases are so good at absorbing and re-emitting the infrared, that the infrared light and all that energy that it carries is just bouncing around the atmosphere until eventually it either gets absorbed back by the Earth's surface or it escapes out into space. the light eventually has to escape out into space so that the energy in equals the energy out. Eventually that'll happen. Eventually the energy in has to equal the energy out. But it does it at a higher temperature. This part of the diagram right here, this is the greenhouse effect, right? The Earth is trying to cool off. The Earth is giving off light to cool itself off. But that light can't escape out into space. It gets reabsorbed by the atmosphere, and then the atmosphere re-emits that light back down to the ground. And when that light gets reabsorbed by the ground, it heats up the Earth some more. So the Earth gives off more light, and it gets reabsorbed. So the Earth heats up even more until it gives off more light, until eventually the Earth has to warm up to a higher temperature so that the Earth can force the light back out into space so that the energy out equals the energy in. The energy balance is reestablished, but it's reestablished at a higher temperature. That's the greenhouse effect, right? If it weren't for the greenhouse effect, the Earth would be a cooler place. We saw when we were looking at the planet properties lecture, if the effective temperature model, if there was no atmosphere, and the effective temperature was the temperature of the Earth would be 250 degrees. And the Earth would be frozen. The Earth would be in a perpetual ice age. But if you add a little bit of greenhouse gases, if you add a little bit of carbon dioxide and a little bit of water vapor to the Earth's atmosphere, those greenhouse gases are so good at holding the heat in and warming up the Earth that it warms up the Earth. That little bit of greenhouse effect warms up the Earth by 30 degrees, and it makes the Earth a nice temperate place with liquid water like we have right now. So a little bit of greenhouse effect is a good thing. The problem today is we're adding more carbon dioxide into the atmosphere. And if we're adding more carbon dioxide, we're making the atmosphere thicker. We're making the atmosphere more absorbent of energy. It's going to absorb more light from the Earth and from the sun and trap that energy on the Earth, which is going to raise temperatures. And we can see what that relationship is if you go back through history, if you go back through the fossil records and look at, well, what is the normal amount of CO2 in the Earth's atmosphere historically? When you go and dig through ice core samples and fossils, fossilized trees and that kind of thing, from all over the world, it looks like over the last, now this data set goes back 800, so the present is over here, and then we're going back 800,000 years. There's some research in the last few years that goes back a few million years, but this is this has a lot more. This shows a lot more detail, so I wanted to look at this one. So over the last 800,000 years, it looks like the amount of CO2 in the Earth's atmosphere varies over slow time scales, right? It goes up to about 250 or 300 parts per million. What am I measuring here? Parts per million. So it's not a percentage because percent literally means per 100. So these are numbers in per million. So it's a very small percentage, right? 300 parts per million that translates to 0.03%. 0.03% of the Earth's atmosphere historically is carbon dioxide. And it'll go down to 200 and then it'll come back up to 100. So there seems to be a natural variation that you'll get more carbon dioxide and then it'll go down and then it'll come up again and go down again. And there looks like here on Earth there's a cycle that happens about every 100,000 years where the Earth will get more carbon dioxide and then plants will breathe in the carbon dioxide and it'll go down and it'll come back up again. The natural cycle of the Earth is to go between about 200 and about 300 parts per million. And then when you get into the modern age, it spikes. Such that today, starting around, well, really starting around the year 1750 or 1800, then the amount of CO2 in the atmosphere goes up way higher than it has for millions of years. Um, we broke 400 parts per million in about 2013. In 2019, 2020, we're over 400 parts per million. Here is the same data, but this is only going back 400,000 years. Here's the temperature of the Earth over that same time period. So what you notice is 400,000 years ago, 300,000 years ago, 200,000, 100,000, the amount of CO2 goes up and down and back up again, and also the temperature of the Earth, the average temperature, the climate of the Earth. We're not just talking about like, oh, the weather on a given day is warmer. No, no, no. The average temperature of the whole planet Earth was warmer, and then it goes back down again, and then it goes up and back down and up and back down. So temperature and CO2 concentration are correlated. When one goes up, the other one goes up. And then it goes down, and the other one goes down. And so here we are today at a point where, starting around 1750, it spikes. And we are at levels of carbon dioxide in the atmosphere that the Earth has not seen for many millions of years. There hasn't been this much carbon dioxide in the atmosphere for, well, at least 800,000 years, but really the data that goes back even farther says it's been millions of years since there was this much CO2. And what the data of the last few years, 10, 20 years has said is that the temperature is going back up too, or the temperature is going even higher. How much of that temperature increase is due to carbon dioxide that human activity is putting in the atmosphere, and how much of it is natural? Because, of course, there are multiple sources of carbon dioxide, right? Volcanoes pump out carbon dioxide. Plant decomposition emits carbon dioxide, but also human activity, right? Burning fossil fuels, burning coal and oil and natural gas. That all produces carbon dioxide also. So how much of the current temperature of the Earth is due to human activity, and how much of it is natural? Well, the nice thing is that over the last 100 years, we've got really good data, right? Going back over the last 100 years, we know how many cars and trucks and power plants have been built. We know how much coal and oil has been burned. Like we've got good records for that. And also over the last 100 years, we know how big the volcanic eruptions have been. We've got all that good data. So you can put this together, you can put all this data together and compare. All right? So this graph looks a little complicated, so let me break this down here. The blue line is what the temperature of the Earth would be if all the carbon dioxide in our atmosphere were from natural sources, like volcanoes. The red line is what the temperature of the Earth would be if you add in human-produced greenhouse gases. So if you add in all the burning of wood and coal and oil and natural gas, if you add that in, then the Earth would be the red line. The black line is the real data. The black line is the temperature the Earth actually has been over the last 100 years. And you can see the black line fits the red line pretty darn well. There is no way to explain. The black line here is the temperature of the Earth these days. Those don't match. There is no way to explain the temperature of the Earth the way it is today based solely on natural sources of carbon dioxide. You have to add in human activity to explain the temperatures that the Earth is today from the carbon dioxide that we emit. So that's why global warming is such an important issue. This is why this is why this is the most important issue in the world, is that we're not just talking about weather. We're talking about climate. We're not just saying, oh, well, the Earth is warmer. How much warmer? Well, over the last 100 years, the Earth has warmed up by 1 degree Celsius, which doesn't sound that bad, right? It's like, oh, the Earth is 1 degree warmer. That doesn't seem that bad. Well, we're not talking about weather. It's not like the weather on a given day is 1 degree warmer. We're talking about climate. The entire temperature averaged over the entire planet from the poles to the equator. The entire planet is 1 degree warmer. How much energy does it take to take an entire planet and make the whole planet 1 degree warmer? A lot of energy. The Earth is holding on to a lot more energy. The atmosphere is holding on to a lot more energy than it was even 100 years ago. When this happened before, right, the CO2 goes up and then the Earth warms up and then the CO2 comes down and the Earth cools down. Yeah, this has happened by natural means before. But look at the timescales here. It takes 100,000 years. The Earth changes by what? From like 4 to -4, -6. So the Earth will change by 10 degrees, but that's 10 degrees over the course of 100,000 years. This is a very slow, gradual temperature change. What we're doing with man-made global warming now is we're taking the Earth and we're asking it to warm up by 1 degree in only 100 years, which is much faster than the Earth has ever had to do. What effects does this have? Well, most of the Earth is covered by water, and water is really good at holding in heat. Water is really good at holding energy. So you're taking all of the ocean water all over the entire surface of the planet, and you're warming it up by 1 degree. What does that do? Well, what happens to water when you warm it up? It evaporates. And then all of this warm, wet, evaporating air drives hurricanes. So that's why the intensity of hurricanes has gotten stronger in the last few years. Then we get to something real scary. We talked in the last lecture about the inorganic carbon cycle and how carbon dioxide in the atmosphere can dissolve in rain and wash into the oceans. How does that happen? How does carbon dioxide dissolve in water? Well, when you take carbon dioxide and you dissolve it in water, it does it by mixing carbon dioxide and water mixed together and form H2CO3, which is carbonic acid. This is the acid in soda pop, right? Why do sodas have bite to them? Why do sodas have some tang to them? And it's because carbon dioxide has dissolved in the water, and that forms carbonic acid. That's the acidity in soda pop. When you open up a soda can and you let all the bubbles come out, what are the bubbles made of? The bubbles are made of carbon dioxide. So as long as your soda can is sealed, all of that carbon stays in the water as carbonic acid. But this is a reversible reaction. This chemical reaction can go in both directions. When you take a can of soda and open it up, all of a sudden the carbonic acid turns back into carbon dioxide and water, and those carbon dioxide bubbles bubble out of your soda and go into the atmosphere. Have you ever drank flat soda? What does it taste like? What does flat soda taste like? It's kind of gross, right? Because it just tastes like sugar water. Because at that point, it is sugar water, right? When the soda is flat, all of the carbonic acid has turned back into carbon dioxide. All the carbon dioxide bubbles bubbled out of the soda, and all you're left with is water. That's why flat soda tastes watered down and kind of gross and sugary, is because all the acid is gone. Well, here we're doing the opposite. By putting more carbon dioxide in the atmosphere, we're dissolving more carbon dioxide in the oceans, When there's more CO2 in the atmosphere, more of that CO2 is going to dissolve into the oceans. And so now the oceans, in the last few years, it's been measurable that ocean water is now more acidic than it used to be. And this is causing some real problems in the ocean because A, the oceans are 3/4 of the planet, but now you're taking all the life in the oceans, all the plankton and the fish and the coral. You're asking all of these animals and plants to live in a hot, acidic bath. Animals and plants that never evolved to survive like this, right? That you've got, you've got these fish that are used to living in, cold water, and now you're asking them to live in warmer water that is also acidic. And they can't swim away from it because it's happening everywhere in the planet. And so you're having mass die-offs of fish, the bleaching of coral, right? You're having huge coral reefs that are dying because all the coral are living in a hot acid bath and they just die, and then the coral reefs die with them. It's not just about the temperature, it's also about the chemistry of the oceans is being messed with by putting all this CO2 in the atmosphere. And then also the melting of the glaciers, right? All the ice caps are melting, which means all of this ice is now melting and flooding into the oceans, and that's also messing with the temperature and the chemistry of the oceans because you're taking all this fresh water, melting it into the oceans, and now the saltwater oceans are becoming less salty. And again, the temperature, the climate, the life that lives in the oceans, it evolved to live in a colder, saltier ocean water, and now we're asking it to be, we're asking them to live in water that is warmer and less salty. And that's not good. Messing with the chemistry of the oceans ends up affecting the climate here on the land too. This is why this is such an important issue. And frankly, I'm going to go on further. This is why this is the most important issue. The most important issue today, and I realize that given the current state of the world, that's a strange statement. But the current COVID virus affects people and bats apparently. This is a Global warming is an effect that influences all life on Earth, in the oceans, in the air, everywhere, all of it. And we're experimenting with the Earth by changing the chemical composition of the atmosphere. We are strengthening the greenhouse effect. We are making the atmosphere more absorbent of infrared light. Infrared light is the important stuff here because that's where most of this energy is. And we're affecting the habitats. We're infecting the living conditions of all life on Earth, not just human life, all of it. What happens? What's the logical endpoint here? Well, we know what the logical endpoint of the greenhouse effect is. It's Venus, right? Why is Venus so hot? Venus is the hottest planet in the solar system, even though it's not the closest. Mercury is the closest planet to the sun, and yet Venus is hotter than Mercury. Why? Because Venus has a thick carbon dioxide atmosphere. And carbon dioxide is really good at absorbing infrared light and trapping that energy to the planet. It's heating up Venus by 500 degrees, and it's heating the Earth up by 30 degrees and climbing. So we know what the logical consequence is, right? The logical endpoint here is that Earth becomes a roasted, blasted planet like Venus is, a planet that is absolutely uninhabitable. Is that going to happen to Earth? We don't know yet. That's the problem. That's why this is such an urgent issue. We know that this is a threat. We think we know how to stop it, right? All we've got to do is stop putting so much carbon dioxide in the atmosphere and then remove what we've already put in and do it before it leads to the point of no return. The problem is we've never run this experiment before. And it's not like we're running this experiment in a nice controlled environment like a lab. We're running this experiment all over the earth. It could threaten all life on earth. There is probably a point of no return where the earth heats up so much that it can't cool itself off again. But we don't entirely know where that point is. This is why this is so urgent. That's why I say this is the most important issue. Because it could kill everything. Everything on this planet. The next century is going to make the decision, because this next century it could mean a little bit of heating, a little bit of global warming, or it could mean a lot of global warming and the utterly catastrophic effects that that'll have. We have the knowledge to reverse this. It's not going to be fast, and it's not going to be cheap. Anybody that tells you that global warming can be fixed cheaply and quickly is lying to you. This is going to take the work of our generation and our kids and our grandkids. This is going to be the project of the next century. And if we do it, if we invest the money, and it'll take a lot of money, and if we invest the time, and it'll take a lot of time, but if we do it, we can save the world. That really is what we're talking about. We're talking about having the courage to do the work that has to be done to save the world. And that's a choice that we all have to make. All I'm saying is it's an election year, so, something to think about.